2 pi over 3, but now we have to power of 3 because we are referring to 3 dimension. So it's just like this. So now, okay, you got to find the number of mode in the sphere of radius k. Previously, we just find the number of mode in one line, okay, in one line. But 3D, of course, you cannot find in one line because now the number of the density of state is in cube 3D. So you have to find the number of mode in one volume, okay, in one particular volume. And the easiest way is that we want to find it in sphere, okay, sphere, so that we can take the radius as k. So let's say I want to know what is the number of mode in this sphere. Okay, first I want to know from this point to this point is k the radius. So the volume for this sphere will be 4 over 3 pi k power of 3, right? The volume for this sphere. Okay, and then the volume of each cube is 2 pi over L power of 3. So now I want to ask you how many cube that we can find in this volume of sphere. How do we calculate it? Very simple. We just use the volume of the sphere over the volume of the cube, right? So the number of mode or number of cube in the sphere of the radius k is given as the volume of the sphere over the volume of each cube. Okay, then to solve it, you'll get this one. Okay, a very simple mathematical calculation. So now we differentiate this number of mode with k. That will give you number of mode between sphere of radius k and k plus delta k. Okay, so we differentiate this equation, then we will get the number of mode between the sphere of radius k and k plus delta k. So very simple differentiation. Then we get this equation. Okay. So the number of mode between the sphere of radius omega and omega plus d omega is also equivalent to this equation. Why? Because k is corresponding to omega. Okay. So in other words, I can say that gk dk equal to g omega d omega equal to this value. Okay. So g omega d omega equal to gk dk equal to this value. Now you want to further simplify this equation 10.14. I can replace that. We know that V naught equal to k or the omega over k, right? So I can substitute this k square. So k equal to omega over b naught lah. So I just substitute k equal to omega over b naught into here. Then I get this one. Okay. Then dk equal to d omega over b naught. I simply substitute k to this one, and then dk by this one. Okay. Why? Because b naught equal to omega over k equal to d omega over dk. Up to here, okay, right? So now we have the density of state equal to this one. So I take out d omega from both sides and then solve this one. So we have b naught times this one. So we have b naught power of 3, then omega square. Then this one we have v, then 4 pi over 2 pi power of 3, we get 2 pi square. Okay, we get this one. And then since we already cancel both the d omega from both sides, so now we only left g omega. And g omega is the density of state. Remember? G omega d omega equal to number of state, and then G omega is the density of state. So the density of state or density of mode equal to V over 2 pi square times omega square times V naught power 3. Okay, this one. This is what we obtain up to here. However, this equation, the equation 10.15, is not exactly true for 3 dimension, because for 3 dimension, each K have 3 mode, 1 longitudinal and 2 transverse. Okay, even for the x direction. Just now we assume, okay, this is what we have in our starting equation. We only consider that the kx is along the x, which is longitudinal, but you also can have the kxy, which is transverse to the x direction, and kxz, which is transverse to the x direction. Okay, therefore, the final equation that we obtain in this equation have 2 times 3. Okay, so this equation we have 2 times 3. Since each k is correspond to 3 mode, 1 longitudinal and 2 transverse. Okay, so we have 3 over 2 times v over pi square blah blah. This is our final equation, or equal to this one. Say, okay, so these 3 modes are assumed equivalent for cubic or isotropic, and therefore have the same sound velocity, and therefore we get density of state equal to this one. Okay, so if we plot this equation into graph, g omega versus omega, then you have the graph like this lah. Right? Y equal to x squared. Smiling. Correct or not? So this is what we get from the theoretical result. However, for the experimental result, this is how it look like. So it doesn't fit very well. I mean, the experimental, the theoretical result or the theoretical modeling doesn't fit well with the experimental result. So now we want to improve all this model. Okay, so this density of state will be used in the Debye theory to determine the specific heat of the lattice vibration later on. So now there are a few slides after this simple modulation. So there are a few scientists like Dulong and Petit. They come out with the classical theory for the lattice specific heat (CV). So their model is very simple. They will just consider there are n atom in one solid or in one system, and each atom has 3 degrees of freedom. Okay, it can vibrate x direction, y direction, and z direction. Okay, so they have kinetic and potential energy as well. So the total lattice energy is given as U equal to 3 N kBT. Okay, so what is kBT? kBT is the average thermal energy per atom per degree. Let's say I have 3 atoms. Okay, so all these 3 atoms have the energy of kBT. Okay, in the classical world, because this is classical theory. However, in the quantum world, each of these atoms will have the energy of omega bar h, bar h omega bar h omega. This is the difference between classical and quantum lah. So, but now we are discussing the classical theory. So we assume that, let's say I have 3 atoms in one system, and all the atoms have the energy of kBT, kBT, kBT. Okay, and each atom can have 3 degrees of freedom. So it's 3 times kBT, 3 times kBT. Okay, so if I have 3 n number of atoms, then it will be 3 n kBT. If I only have 2 atoms in the system, then I will have 3 times 2 times